afternoon to all distinguished members of the panel and all other audience. My name is Anit Zakina binti Muhammad Sarafia and I am a seed student from SKKU. So rapid synthesis of silicon oxycarbide as SiOC coating on bismuth nanoparticles in a supercritical fluid for superior lithium storage is the title of my presentation today. To uncover the title of today's topic, I will briefly introduce four main parts, which is the research background, research procedure, results and discussion, and lastly the conclusion. Evolution of battery development in the automobile segment has drastically increased, expecting that the demand of electricity from EVs to increase by 35% by year 2040. But however, lithium-ion batteries, despite having a superior performance, they lack in the usage of large scale energy storage systems, such as the electric vehicles, due to problems of scaling up issues. Respected to the cost and also safety and also the energy enhancement. Thus, it is basically necessary for us to modify the lithium-ion batteries, the main parts, which is the electrode and also the electrolyte. So basically, these are the general approaches of improving the performance of LIBs. Depending on the mechanism, we have three types of electrode, which is the insertion, conversion, and also the alloying material type. And downsizing to a nano scale is very important because it can help in aiding the lithium-ion diffusion, but there is issue on the surface energy which is high. Thus, the nanoparticles tend to agglomerate. Thus, in many cases, the nano sizing is accompanied by nanostructuring. And also the optimization of the binder and also the electrolyte is necessary because they can help in controlling the structural morphology from collapsing. In this mean, most of the coating material or the active material is altered to solve the previous issues just mentioned. So our approach in this research is to use bismuth and silicon oxycarbide by applying all the mentioned modification by a simple one-pot supercritical method. Bismuth actually is one of the alloying material that is very appealable because it has a small volume expansion compared to other alloying materials and also a high volumetric capacity. But like other alloying material, it tends to expand, causing cracks and pulverization upon lithiation and delithiation. So the issue to solve this is usually by using a coating material, either a carbon or also SiOC. But the issue is that carbon-based material the structure is very rigid, so it tends to break or collapse upon cycling. Thus, our introduction is this by coating of silicon oxycarbide with silicon oil. The issue in silicon oxycarbide coating is that most of the precursors used are very complicated and it takes a long time. That's why we suggested using silicon oil in a simple process just by pyrolysis. Following to that, the issue why we chose supercritical fluid to produce bismuth silicon oxycarbide composite is that because, as you can see in front, the supercritical fluid has a lot of combination of good properties, and this allows the nucleation of the nanoparticles instead of the crystalline growth. So we can maintain a small size bismuth nanoparticles with a narrow distribution of size. Here is the research procedure. So basically, we did a simple method by mixing the precursors of bismuth nitrate pentahydrate in acetone with nitric acid, followed by a homogeneous mixing with silicon oil. Supercritical is then done for 10 minutes, followed by a two pyrolysis step at 120 degree and 500 degree. This is actually to allow for structural rearrangement and also for crystallization. And for the results and discussion, our samples, supercritical bismuth silicon oxycarbide, is denoted as SC, bismuth SiOC, while SC bismuth is only the bare samples without silicon oxycarbide coating. As you can see, the crystalline size is quite small, 42.4 nanometer, compared to the one without this SiOC coating. And even from the VET data, it can be seen that we have a mesoporous structure. And to actually prove that the nanostructuring of our method is very good, we produced a simple step of bismuth silicon oxycarbide using a dispersion method, which means that we dispersed the bismuth precursor into silicon oil. As you can see, even though the crystalline size is quite low, which is 23.7, from the electrochemical performance, you can see that it's low compared to the method that we use using supercritical fluid. And from SEM and TEM, we can see that we produced a hollow rod-like structure, and the bismuth nanoparticles is embedded within the structure. And also from TEM, it can be observed that we have a double coating layer, which means that the SiOC and carbon from acetone is both formed on the bismuth nanoparticles. And then moving on, I mentioned previously that optimization of the binder or the electrolyte is necessary. So in this case, we compared PVDF binder with CMC binder, and as you can see in the blue line, there's a drop in the capacity when the current density is high, which means that the PVDF cannot provide or retain the structure of the bismuth silicon oxycarbide. And then lastly, from the CV, we can interpret that the samples undergo a two-phase transition from bismuth to lithium bismuth, and then followed by to lithium 3 bismuth during discharging, and then a single phase transition during charging. So to summarize, our research actually introduced a new technique in producing bismuth silicon oxycarbide composite by a simple method, just mixing silicon oxycarbide with the precursors for SiOC coating and also for carbon coating. And then for comparison with the conventional graphite, we also did a calculation on the volumetric capacity, and we can see that our sample provide more volumetric capacity compared to the graphite. Thus, in conclusion, our research provides a new pathway for the production of a high performance bismuth alloy-based materials for anode in LIBs. So with that, I conclude. I finish my presentation. Thank you.